as we are not doing any experiments or something, so I just planned something which we can do online. Okay, so this is kind of outline for that, and we go directly what we do in research. Okay, so there are many tasks what we do. Okay, but all the tasks are interrelated, and those tasks we do differently, but they all contribute to the one kind of like relation between. For example, we do synthesis, we do characterization, and we do analysis. So all things will be enabling us to let us know what we are doing in research. Okay, so this is what we use for our research. Means it is a 3 electrode cell. Okay, so you have learned about this in your courses. Okay, but in actual physical form, it looks like this, right? So
Mm.
you see, I show you my pointer. Yes. So can you tell anybody what is this particular thing is? This particular board?
Working electrode.
No, this is for gas inlet. Means if we want to saturate this particular electrolyte, we pass the solution from this gas in, and after bubbling here, the gas will go out from this port. Okay, so that is called gas purging inlet for our 3 electrode cell. In our like simple diagram, it will be like 3 electrodes, but in actuality or in practice, that is not the case. Okay, it has to be completely sealed, and there should be a saturating gas for the electrolyte. So this inlet is there, so you can see this, it is gas tube is connected here, and gas goes in and gas goes out after bubbling inside the electrolyte. Okay, and then this is the one electrode is there, this line. Okay, can you tell me what is this?
Reference electrodes.
Which one?
Reference electrode.
No, it is counter electrode. Okay,
Um, oh,
counter electrode is like a platinum wire inside some glass tube, right?
right.
Yeah, so you can see it is connected to the instrument by these connections, and you see this one. This is what is called a reference electrode. Okay, and you know there are different kinds of reference electrode, and this particular reference electrode is hydrogen electrode. Standard, what do you call it? SHE. Yes.
Yes.
Yeah.
Yeah, so you see this black cap on the top of that, it is a hydrogen cylinder. Okay, so it supplies continuously gas to this electrode tip, so that's why that way it will have like standard potential all the time. So that is what we use as a reference electrode. Is still all is this is only concept, but when we go into lab, you can see this by touching how it looks and how it feels. Okay, and there is a one rod here, you see, at the back of working electrode, this one. This is kind of motor. Okay, this is motor, and this is rod connected to that motor, and this is dipped into the electrolyte. Okay, so this particular motor, what it does, like it rotates this rod. Okay, on top of this rod, we attach this one. This is called RDE, rotating disc electrode. Okay, so here, what we do, you see black part here. Okay, this black part is graphite electrode. Okay, so onto that graphite electrode, we put our electrode, new materials what we synthesize on top of that, and then we put it onto the rod. Okay, onto this rod, and then we connect all the instrument together to characterize this kind of electrode. So what we did in presentation was like everything what we do, but our research direction was to know what kind of materials is how it works. So to know how it works, we have to do this kind of characterization. Okay, so we make a catalyst and we put onto that black part, and then we connect this to the rod, and then we start our experiments. Okay. So this is to give you idea, means we put some research direction during presentation, but we don't know how we do that. Okay, this is just to give one example. Okay, this is just one example of characterization, and this is what we do, and this is very most important in our project. Okay, because we do some electrochemistry all the time, so this kind of setup is always used when we do characterization. So this all particular setup is called rotating disc electrode, uh, and all the assembly is called measurement is called thin film rotating disc electrode measurements. Okay, so this is very fundamental technique for our kind of research. Means when we do catalyst synthesis and we do characterization, and it is done by only this kind of method. It is used for ORR characterization. You know, all of you explained during your presentation this ORR characterization or ORR catalyst. Okay, so that catalyst is only characterized by this kind of experimental technique. So that's why it is very important in our research, and so it is usually preferred how we do it. Okay. So, but this is only experimental cell, okay, and we have to connect it to the instrument so that we can measure the experiments, right? So, if you see, yeah. So you see where is that cell now, right? The cell is here, okay. You see cell.
Yeah.
Yeah, so from the cell, from the electrodes, counter electrode, reference electrode, at working electrode, all the wires goes to potentiostat. Okay, and this potentiostat can control this current or voltage, and we get also measure the current and voltage. But it is a very fast process. So usually this electrostat is connected to the PC, eh? And PC is having some software specific to that instrument, so that it can control this instrument, and via instrument it can control the voltage and currents inside the cell. Okay.
Okay.
So this software is only specific to this instrument, right? But we use this instrument. It is called rotator. So to rotate our electrode, so that the electrolyte flow will be continuous onto the spot. So I'm giving this because this is the basic concept how you will do experiments in your projects. Okay? So you will prepare some electrodes materials, put it onto this electrode, then connect to this system, and then you set some speed at rotate, okay, using this instrument, and then you give instructions on PC, and then the PC will start doing measurements, and then it stores on the PC. Okay, and then this data you will take into Excel or Origin. Origin plot is one software to analyze the data, and then you will analyze the data to know how your catalyst is performing. Okay,
Okay.
are you getting, or it is going like, on top of your head? You can ask me anytime. Okay.
Yeah.
Yeah, so you can stop me and you can ask me. It is just to let you know how we do research in our particular project. Okay? So here you see this is like there is one equipment here, one equipment here, one equipment here, and one more is we need to purge the gas through the electrolyte. Okay, so we need to manually switch on, switch off the gases because for oxygen reduction reaction we have to supply oxygen. Okay, but when we want to know the surface area of catalyst, we has to supply argon, not oxygen. So we have to switch gases from argon to oxygen, and then we have to wait for some time to purge it, and then to make it saturate, and then we do measurements, right? So this is a very long procedure to do experiments, right? And usually it has this many steps. To characterize one sample, you do like 15 steps, right? Okay, so
Oh,
I know it's too long, but it is not that much. Okay, you see these are the switching oxygen, switching to argon, switching to argon, switching to oxygen. Okay, so this you see light red color. This is like mechanical steps. Okay, now I will give you presentation. No need to take screenshot. Okay, see.
oh, okay.
Okay,
Mm,
so these are like mechanical steps which you can do manually, like switch on, switch off. And these rate steps are all done by that potential stat I told you, that particular instrument, right? So we have to like start like give data input into the software, and it will take that data and pass it to the instrument, and then instrument will start doing measurements. So once we do this one, then we have to switch to oxygen. So the instrument cannot control all the process at the same time, right? Okay. So it will do this all three because three are the same kind of measurements on the one instrument. So it can do these three together. But to do this, we have to do manually, right? And then it can be done by instrument itself, and then we have to do it manually again here. Then it will be done by instrument, this thing. Then we have to done manually. Then it will be start by instrument, and that is finished. So this is just to collect the data. Okay, this is just to collect data. So how much data we will collect after these experiments? You see, all of these measurements are kind of cyclic voltammetry. Okay, then you raise your hand. Any questions?
Yes. I mean,
Yeah.
what's the ESA or this
Yes,
means?
I will tell. So ESA is like electrochemical surface area. So we do one character.
What's that?
Electrochemical surface area.
Electrochemical. Okay.
electrochemical surface area.
Yes.
Okay.
Yeah.
Okay.
So
And what's OR?
Yeah, I will tell you one by one. Okay. Now,
Oh, okay. Okay. Thank you.
so this activation is called we activate the electrode material inside the electrolyte. So how we activate? We do cycling. I mean cycling voltammetry. You heard of that?
Yeah.
Yes. So we do one technique of electrochemistry. It is called cyclic voltammetry, where what we do basically, we just ramp the voltage across the electrode, like go from one point to another point, come back and do some cycle. Yes.
Yeah.
So that is called cyclic voltammetry, right? So all these red points here you see on the slides are all doing the cyclic voltammetry only. But when we do that cyclic voltammetry, it gives the results different. Okay, so that's why first we do activation of our electrode material inside the electrolyte, and that way whatever the impurities on the electrode surface is there, it is destroyed because of that cycling, right? Then the electrode surface becomes very clean. Then we do ESA cycling. Okay, so we do cyclic voltammetry, right? And with the cyclic voltammetry using for this particular characterization, then we extract the data of electrochemical surface area from that kind of cyclic voltammetry, right? And this ORR, it is called oxygen reduction reaction. Okay, so this characterization is particularly used to know how your electrode is performing as a cathode material inside the electrolyzer. Okay? So you will get a cyclic voltammetry for this, and that is used as a background for your characterization, right? And then you go to switch oxygen, and then the reaction will happen in oxygen atmosphere in the electrolyte. And then we characterize the ORR for measurements. So this is ORR in argon atmosphere as a background. Then we switch it into oxygen, and then we do again ORR. So by subtracting background, we get how much activity of catalyst is there for oxygen reduction reaction. Okay, so these two steps are to know how active is your material for oxygen reduction reaction. Okay, And then we go to switch the argon, switch it again argon, and then we do some ESA testing again by cyclic voltammetry, and then we do this kind of step. It is called stress test. Okay. By this test, we know that how much long this catalyst can survive. You see, there are like 7,500 repetitions of these stress cycles. Okay. So we do a lot of cycling. Sometimes we do like 30,000 cyclings, and then we do a test again its surface area. So we know that when we cycle a lot of times, its surface area goes on decreasing. Okay. So we want to know how active the catalyst remains after 7,500 cycles, right? So for to test that, we do this. Okay. And then we go again to measure the ORR background, switch to oxygen, and then again we measure the ORR again. Means that after doing stress test, how is its oxygen reduction reaction activity remains or it loses. So we know that after stress test what happens, before stress what happens, and how was everything before, as a new electrode, how it worked. So that characterization we do by assuming how is active our surface area of catalyst. Okay. So by these kind of measurements, we know how active is our materials for as a catalyst for ORR, right? I know it is very much. It is just to give you like how many steps we do manually if you want to do manually, okay? Right? So don't think about this right now. It is just to know that there are many steps we do, and we do few extract the data from this kind of characterization. Okay. So there are basically 5 kind of cyclic voltammetry inside this particular characterization. Okay. So one is cyclic voltammetry for activation, one is cyclic voltammetry for electrochemical surface area, one is cyclic voltammetry for ORR reduction, okay, ORR, and then for stress, and then again for during the stress, how the surface area will change or decrease. But if you see here, means I calculated the time for each of the cyclic voltammetry. You see, it is 8 minutes for here, 7 minutes for here, 6 here, 50 minutes here, 8 here. And as we go for cycling, it goes very high. Okay? So you see how long it will take, almost 30 hours for one measurement. Okay. So can you able to stay there in front of that machine for 30 hours continuously? No. Okay. So that way, even we do a simple characterization, one simple characterization for a research, we have to do some experiment about 30 hours for one catalyst materials. Okay. So yeah, and you see here what kind of data we get after all this characterization. So we do cyclic voltammetry is like this. You see, here is a current and here is a potential. We change the potential, okay, like this. Go to the end and come back. Go to the end and come back. Okay. So this is cyclic voltammetry, right? So this you can see there are numbers. I will tell you. It is like for 7,500 cycles. Okay. So there are cycles of 250 cyclic voltammetry as neglected, and after 250 cycles they measure 1 CV and record it here. Okay. So using this cyclic voltammetry, we calculate the surface area of our catalyst, right? So using this kind of calculation is, for example, if you see from 0 and for this particular area, okay, it is expanded this side. And using this particular calculating the what you call area under the curve, we can know, and we use some formula, and we can calculate the surface area of our catalyst. Okay. For example, this particular catalyst had like 41.75 meters square per gram as an electrochemical surface area. Okay. So this kind of data you have to compute for all these 30 cycles. Okay.
Mm.
Yeah, you can ask me doubts if you have. Okay. So these all 31 cycles, you can see I showed it here. You see 750, 1500, 2250. These are the cycle numbers. Okay. And I calculate the surface area for each of this graph. Okay, using each of graph, and I plotted as like this. So 100% was the first surface area, okay, at the first point when we had a zero cycling, stress cycling, and then as we increase the stress cycling, its performance goes down, right? So this is called a stress curve, means like how your surface area behave with the stress. So if it is going down, it's not good catalyst, okay? If it is staying straight, it's better. Means even you have like 7,500 cycles and you get like 99% of performance or surface area, it is good. But it is going down, it's bad. Okay. No need to understand all the graphs. Okay, I will explain you later. This is just to show you one kind of measurements what we do and how many things we have to do to obtain the results. Okay. So you see the loading wise, we had the surface area. So you understand that, okay? So you have to calculate the surface area for each curve, and you have to measure a lot of curves, and you have to make a data analysis from that curves, okay? So these are different steps inside your, what you say, inside your characterization, for one characterization, okay? By doing all this characterization, you can say that whatever you material prepared, how it was for your particular applications. Yes, if you do all this kind of experiments for one material, you can tell for sure that this material has this kind of properties, like it will perform for longer time, or it will have a very better activity or something like that. So this is particular one method of characterization by which you describe the catalyst and its performance. Okay, it is for catalyst performance, not for electrolyzer performance. Okay, you know that, right? When you presented, you told that how to perform this characterization of cell and how to perform the characterization of particular material in a half cell or 3 electrode cell. Okay. So this is how we characterize the prepared material. So I am not telling anything about how we prepare the material. I am just telling you how we characterize the material. So once we fabricate the catalyst, we do this kind of characterization and we get this kind of data, and we report it like how this material was performing as electrocatalyst or oxygen reduction reaction. Okay. So this part is one example of material characterization, means different tasks, and one of the tasks is characterization of your material. Okay. So if you are one guy in one project, you have to do all of these alone. But if you have like 3 or 4 guys, you can distribute the work, right? But even after distributing, it will be very hard, right? Yes. So a lot of experience, a lot of data analysis, and doing in Excel, and then plotting the graphs and these things. Okay. So how to escape such a difficulties? Means this is where I come in. Okay. This is our target was there. So you know the basics what we do usually to characterize the material, right? So these are the various steps. But how we can escape this kind of, I mean, this is like working as a robot, right? We are not robot, we are human. So we don't want to waste time for doing these repetitive things all the time together, right? So in last research area where I was working, everybody was doing it manually. Means they was doing like setting the experiment today and they're coming tomorrow, and then again setting the next experiment and then coming tomorrow. So that was like very long procedure. They used to take 1 week for one characterization, right? Then how to escape such a difficulty? So because I had like some experience with some automation, okay, automation of doing experiment automatically. So I proposed them and I said that, yeah, these experiments can be done without interaction of human being. Like you set all the settings once and you go home. So you don't need to look back at what is your instrument is doing, right? So this is what I did. Means I'm little bit lazy about doing same thing again and again, right? So what I did, like I tried to use some automation techniques, and by that I was like trying to do all those things automatically. And so next day when I will come, I will just take a data out of the instrument. So I will just give you an overview of what I did. So you will know the idea means like what you can do yourself, right? So this is what I did. It is called automation of TF-RDE experiment, right? So you see your experiment setup is here. This rotor is here, cell is here, and potential stat is here, and is connected to the PC, right? But what I did, like when you have any instrument connected to your PC, you can control it for sure. So if you have little bit knowledge of how to control that instrument, according to your sequence, you can program it and you can tell that instrument how should you work. But not all the instruments are directly connected to the computer, right? Few of them are like you have to do manually, like switching off on and off the gases, right? That you need to do manually. But and also the changing the speed of rotor, you have to do manually, like you have to change the knob so that you can set the rotating speed. But what I did, like I tried to I tried to connect that instrument to the PC. Okay, so there is a company called National Instruments, right? So that National Instruments provides LabVIEW software and some hardware which can make you connect this kind of machines which are not able to connect to the computer via that particular tool. For example, you see here, you see this particular clock, right? This is called DAQ instrument, right? It is called data acquisition system. So via that, when I connect some wire from this rotor instrument to this, and this instrument is directly connected to the PC via USB, okay? So that way I have now connectivity with that rotor via that National Instruments part, which can be connected to the directly computer, right? So now I am connected to that instrument via USB. So if I know the programming, I can control that instrument also. Similarly, I need to switch on and switch off the gases right now, okay, manually. So if I have some instrument which can connect to the PC and I can control from PC and switch on, switch off that gases valves, I can make it happen with program also. So we know there are valves, okay, valves, you know, valves, VALVES.
Wolves.
You know, valve.
Yes, wolves.
Yeah, I
Yes.
write this spelling.
It's like some switch to control the gas to flow in or flow out.
Yes.
Something like that. Yes.
Yeah. So that there is like manual switches and there are like automatic switches, like gas solenoid valves. Okay. So I use those valves and then I connect it to the one instrument here. It is called digital switch instrument. Okay, which is coming from computer National Instruments part, and via this, which can be directly connected to the PC. So right now I have the one structure which can control all the equipment I want to connect to the computer, right? So this way I was able to connect all the instruments to the computer, and now I have to do just coding or programming. So I can control all this equipment according to my way. So I showed you that cycle, right? How it was the 15 steps, right? So I know the steps, okay? And I have already connected all those pieces to computer. Now I have to make some programming so that so that you can control that all the equipment at the same time, right? So I created one script. It's called like sequence of programming, and these steps will be used to control the equipment sequentially. Like for example, what I had the sequence before, that same sequence I can give it to computer, and the computer will do its own. So I will come tomorrow and take the data out of that computer. Okay. So that will be done by this software. I designed this software. You see this particular screen here. That was designed by me. So I can able to control the potential state. I can control this rotor using this particular instrument, and I can control the gas valves using this instrument. So I designed this, and then we had yeah, this is what we had. Like means we had like 15 steps, right? So I use those 15 steps and I make a flow chart of that. You know flow chart, right?
Yeah.
Yes. Yes.
Yeah. So I made a flow chart and I give that sequence to PC through LabVIEW, and the LabVIEW done its all other things. And I just like once I put the data inside, what kind of cyclic voltammetry I want, and how much time the gas purging should be there, and when it should be switch on, switch off, and how the data should be saved. So everything was like automatic. Now I just put like start here. Okay, I start the software and then it do the connections, and I press it start here, and that's it. Then I come tomorrow and collect the data. Okay. So this is kind of software what it looks like. Okay, just I make a few slides with that. So when we start, this is the software which controls the potential state. Okay, this is software which controls the potential state, and I use LabVIEW to put it inside the LabVIEW, so I can control the software also. Okay, so LabVIEW is so powerful that it can use to control the another instrument, but also it can use the another software to control. Okay, so I take control of that software and I ask it to start it, and then when I give the sequence how to perform, it start the instrument here, and you see this particular block, it is to control the gas valves. Okay, here it can control when argon gas is on, this will be on, and when oxygen is on, this will be on. And then here is the rotor control. So I set the speed of 1600 RPM. It will set it and it will keep controlling all throughout the experiment. Okay? And this is the data I have to give them, that software. Like once I put all values, I say done. Okay, I press it done here, and then I start doing experiment. It will start doing experiment itself. So I don't need to have look back to that instrument until tomorrow. Okay, so it does the instruments, and I said the one part, like one part is controlling the instrument, and another part is analyzing the data, right? So instrument control is done by LabVIEW, very good, right? But how to analyze the data automatically? So that LabVIEW also provide you the way to do automatic data analysis also. So I use that aspect of LabVIEW and I put it in here, and you see here this particular button, okay? One click analyze, right? So when I start that, when I press that, you see this kind of window comes out, and it will do all the analysis in one shot. So I just have to click one time and all the data is ready to analyze, and it is analyzed already. So, okay, so I did like control the instrument, I collected the data, okay? I stored the data and then I analyze the data also. But when we do research, we don't stop there, right? We analyze the data, but we need to make a report also. Then reporting this data will also take some time, right? So how about automate that also? So I did that also with using this one, automation of data analysis and then data reporting also. So when we finish this analysis, there was one button I made, and which was able to like do analysis itself. So there is a one video I will show you. You see, the data file I created is here, the Excel file, right?
Yeah.
You see, there are like many files combined together. So if you see the data file is in Excel, not in Excel, it is in usually in TXT file, text file. Okay. So this text file was opened by LabVIEW, and then it is converted into Excel, and then it is making report of that file. So it is not only the data file, it is analyzed file. So what we usually do, means what previously we did was like analyze the data one by one, 30 times. But by this software, all the data was analyzed in one go, okay? And all the report was in Excel sheet. Okay, so so this data was collected here, and there was one more automation I did where it used all the data from all the sheets and created these graphs. Okay. So in earlier section, I showed you the data we analyzed and what we get information from that. So everything was like here. So I got it all automated, right? If you learn that LabVIEW, this is fruit of LabVIEW. Okay, so what I showed you, this is fruit. You have to work hard to know that, and then you will have that lot of benefits from that. So it's very easy programming, and it is like picture programming. So you will see like there are drawings, and by drawing you can control your instrument or your PC or your data files, and you can do it analysis also inside the lab. Okay. So go back to presentation, and I will give you an example. Okay, how we can do it by lab. So I showed you like. We need to control this particular instrument by LabVIEW, right? So we cannot control, we cannot connect this particular rotator to the PC. So we use this kind of intermediate hardware so that we can connect it to the PC, right? So when we connect this thing to the PC, we know that it is connected to the PC, and the LabVIEW will know about that also. So LabVIEW knows that this instrument is particularly connected via this, and we can give just instruction to that particular hardware. So this is what it looks like inside the LabVIEW, right? This is very simple. Whatever it is on your screen, only that was the coding which was used for controlling the rotor. Okay. I know it is not like how to read. You don't know. I will tell you about that. Okay. So you see, I make this control. Okay. Here is the what is current reading of that rotor. Okay. And here what I want to set the rotor at. Okay. So here this particular block you see. Okay. This block. LabVIEW knows that this block is means we will tell the LabVIEW that this block is this particular the intermediate hardware which we use to connect the rotor to the PC. Okay, so when we connect to the PC, the LabVIEW knows that that hardware is there, and you can use it to like control it to another instruments. Okay, so it gives you block like this. Yes, you can ask me anything. Yeah, any questions? Doubts? I will tell you about how it is done, okay, inside this block diagram. Okay. So this is front face of the program via LabVIEW. Okay, these both are same. Both pictures are same. One is at not running, and one is running at setting RPM. Okay. So you see this line you see here, yellow line. Yes.
Yes. Yes.
Yeah, this line, yellow line, is a sequence of steps you want to do to control your rotor. Okay. So if you go via line this is the uh, core of LabVIEW. Okay. So LabVIEW, what it does, like it do anything in sequence. So you have to program it in a sequence. Okay. So to program in sequence, we make a sequence of programming by connecting this line. Okay. First here, what it does, like it is reading what is current reading of your instrument from this. Then I used to calculate it and I put it here. Okay. The setting RPM, right? And then I calculate something, and I used to put, like, if it is higher or greater, you set it here or you just mention it here. So these are the 2 points, right? Set RPM and setting RPM. This is front face of LabVIEW is this, and back end is like this. Okay. You know, when you see one instrument, okay, for example, you see digital multimeter, okay, you see button and you see indicator, right? You tell me yes or no. Okay. Yeah. You see one buttons and you see indicators, right? So
Yeah.
this is button, right? This is button and this is indicator. But inside a digital multimeter, there are like electronic circuits. Okay. So you have the power of LabVIEW to design that electronic circuit, and this is the electronic circuit of that digital instrument. Okay.
Why there's a two different sets? One is
Which,
setting, another is set.
yeah, setting to show that the speed of rotor is increasing. Suppose if you want to set at 1600, the rotor will go from 0 to 1600. So you want to control that speed also, right?
Okay.
If you set like from 0 to 1600, there will be jerk, very fast.
Ah, okay. It's just
If
like
it is
a.
very fast, it will spill out
Okay.
all the electrolyte out of the container.
Okay.
So
I know.
what I did before that also means when we started, I did that like I start from 0 to go to 1600 in one go, and I suffered from that experience because the electrolyte was thrown out. So we have to control the rate how it goes out, right? So I make this. You see this particular. What is that? Yeah, this case you see. This is while loop. Okay, this is loop.
Yes.
So,
Yes.
yeah, I set one rotating speed. For example, here I set like 500. Okay, so it goes 500, right? So the condition of stopping the rotor speed is 500 now. And then we start increasing by 1 RPM. Like we go like 20, 21, 22, 23, right? So it checks condition every time in every cycle. It increases 1 RPM and check if it is 500. If no, then again increase. If it is still less, then go again and increase. Go again and increase.
Ah, okay.
So this way I can control the speed of the rotor, right? So this is what you do simply, like you do calculations and you put it on a block diagram of LabVIEW, and you can design the program which can control the rotor. It is so simple, right? Yes, it is just programming, right? You can do it calculations and you do draw some diagrams on your PC, and it can control your real life instrument. So that is power of LabVIEW, I am saying. Okay. So that is so interesting inside that means This is only I showed an example of like controlling the instrument, but if you want some calculations which are more repetitive, you can do it here also. Yes, for example, you have to calculate like big function, but take data from different files, right? So you can put in while loop to read the data, analyze the data, and put it in some report. So what I did when analyzing the data we acquired during the experiments. So this is very simple. So we put the block diagrams and then we do just programming, and whatever the power of LabVIEW, it will help us during this. So showing all of this is to tell you that this kind of learning skill is not limited to your research project, or you can use it for your own work also. For example, if you want to write same sentence like 10 times in a Word file, you can use this software. This is just I'm giving example. Okay? You can have different ideas and you can implement. It is like giving you power to control the power of hardware. Like PC is more powerful, right? For doing manual work, which we can do repetitively, but humans cannot do repetitively for a long time, but instruments can do. So we just give them instructions and they will follow that instruction. Okay, so that is possible by this LabVIEW. So I will be like very happy to give you lessons about this. Okay, so that's what I am presenting here, that you guys are, if you are interested, we will be like, I will give you guidance to how to go with this LabVIEW, and we will learn something new. So use free time for LabVIEW training, right? So this was my final aim of my presentation. Okay. So these other experiments or every examples I give you just to direct you to this particular slide. So let's have some free time and learn something. How about we do this? Okay. How about use free time to learn? Okay. So to learn, the LabVIEW is for free. Means if you go for like a National Instrument site, and you have to just make your profile onto that site, and they give you free software for your learning. Okay, so this is called Community Edition. Okay, so you get a Community Edition and you can do your own learning on your time. So they have no restrictions for that, but you cannot use it for like commercial purpose. Okay, so for learning it is free, but doing this we will have our own benefit. Like you will learn new skill, and you can use it for any purpose, like for your own data analysis or your own like home projects. For example, if you want to make a remote control for your fans or something, you can do it with LabVIEW. Right? And there are small hardwares which are very cost effective, which can be connected to your PC via LabVIEW. So you will have like more flexibility of working with this. Okay. So any questions now? Okay.
Where do I get LabVIEW? There is any like any like something like trials version? Because
that's what I was telling in last slide. If you go to yanai.com, yeah, yanai.com.
Okay.
Yeah, and you have community edition. Okay.
Community edition.
Yes.